In mathematics, management science, economics, computer science, and bioinformatics, dynamic programming is a method for solving a complex problem by breaking it down into a collection of simpler subproblems, solving each of those subproblems just once, and storing their solutions, ideally, using a memory-based data structure, the next time the same subproblem occurs. Instead of recomputing its solution, one simply looks up the previously computed solution, thereby saving computation time at the expense of a modest expenditure in storage space. The technique of storing solutions to subproblems instead of recomputing them is called memoization. Dynamic programming algorithms are used for optimization. A dynamic programming algorithm will examine the previously solved subproblems and will combine their solutions to give the best solution for the given problem. The alternatives are many, such as using a greedy algorithm, which picks the locally optimal choice at each branch in the road. The locally optimal choice may be a poor choice for the overall solution. While a greedy algorithm does not guarantee an optimal solution, it is often faster to calculate. Fortunately, some greedy algorithms are proven to lead to the optimal solution. For example, let's say that you have to get from point A to point B as fast as possible in a given city during rush hour. A dynamic programming algorithm will look at finding the shortest paths to points close to A, and use those solutions to eventually find the shortest path to B. On the other hand, a greedy algorithm will start you driving immediately and will pick the road that looks the fastest at every intersection. As you can imagine, this strategy might not lead to the fastest arrival time, since you might take some easy streets and then find yourself hopelessly stuck in a traffic jam. Sometimes, applying memoization to a naive basic recursive solution already results in a dynamic programming solution with asymptotically optimal time complexity. However, the optimal solution to some problems requires more sophisticated dynamic programming algorithms. Some of these may be recursive as well but parametrized differently from the naive solution. Others can be more complicated and cannot be implemented as a recursive function with memoization. Examples of these are the two solutions to the egg-dropping puzzle below. Overview. Dynamic programming is both a mathematical optimization method and a computer programming method. In both contexts, it refers to simplifying a complicated problem by breaking it down into simpler subproblems in a recursive manner. While some decision problems cannot be taken apart this way, decisions that span several points in time do often break apart recursively. Bellman called this the principle of optimality. Likewise, in computer science, a problem that can be solved optimally by breaking it into subproblems and then recursively finding the optimal solutions to the subproblems is said to have optimal substructure. If subproblems can be nested recursively inside larger problems, so that dynamic programming methods are applicable, then there is a relation between the value of the larger problem and the values of the subproblems. In the optimization literature, this relationship is called the Bellman equation. Dynamic programming in mathematical optimization. In terms of mathematical optimization, dynamic programming usually refers to simplifying a decision by breaking it down into a sequence of decision steps over time. This is done by defining a sequence of value functions v1, v2, vn, with an argument y representing the state of the system at times I from 1 to n. The definition of Vn is the value obtained in state y at the last time n. The values via earlier times I equals n-1, n-2, 2, 1 can be found by working backwards, using a recursive relationship called the Bellman equation. For I equals 2, n, vi-1 at any state y is calculated from vi by maximizing a simple function of the gain from a decision at time I-1 and the function vi at the new state of the system if this decision is made. Since vi has already been calculated for the needed states, the above operation yields vi-1 for those states. Finally, V1 at the initial state of the system is the value of the optimal solution. The optimal values of the decision variables can be recovered, one, by tracking back the calculations already performed. Dynamic programming in bioinformatics. Dynamic programming is widely used in bioinformatics for the tasks such as sequence alignment, protein folding, RNA structure prediction, and protein DNA binding. The first dynamic programming algorithms for protein DNA binding were developed in the 1970s independently by Charles Delisi in USA and Georgy Gursky and Alexander Zasadatelov in USSR. Recently, these algorithms have become very popular in bioinformatics and computational biology, particularly in the studies of nucleosome positioning and transcription factor binding. Dynamic programming. In computer programming, there are two key attributes that a problem must have in order for dynamic programming to be applicable: optimal substructure and overlapping subproblems. If a problem can be solved by combining optimal solutions to non-overlapping subproblems, the strategy is called divide and conquer instead. This is why merge sort and quicksort are not classified as dynamic programming problems. Optimal substructure means that the solution to a given optimization problem can be obtained by the combination of optimal solutions to its subproblems. Such optimal substructures are usually described by means of recursion. For example, given a graph G equals the shortest path P from a vertex U to a vertex V exhibits optimal substructure. Take any intermediate vertex W on this shortest path P. If P is truly the shortest path, then it can be split into subpaths P1 from U to W and P2 from W to V such that these, in turn, are indeed the shortest paths between the corresponding vertices. Hence, one can easily formulate the solution for finding shortest paths in a recursive manner, which is what the Bellman-Ford algorithm or the Floyd-Warshall algorithm does. Overlapping subproblems means that the space of subproblems must be small, that is, any recursive algorithm solving the problem should solve the same subproblems over and over, rather than generating new subproblems. For example, consider the recursive formulation for generating the Fibonacci series. Phi equals phi minus 1 plus phi minus 2, with base case f1 equals f2 equals 1. Then f43 equals f42 plus f41, and f42 equals f41 plus f40. Now f41 is being solved in the recursive subtrees of both f43 as well as f42. Even though the total number of subproblems is actually small, we end up solving the same problems over and over if we adopt a naive recursive solution such as this. Dynamic programming takes account of this fact and solves each subproblem only once. This can be achieved in either of two ways. Top-down approach. This is the direct fallout of the recursive formulation of any problem. If the solution to any problem can be formulated recursively using the solution to its subproblems, and if its subproblems are overlapping, then one can easily memorize or store the solutions to the subproblems in a table. Whenever we attempt to solve a new subproblem, we first check the table to see if it is already solved. If a solution has been recorded, we can use it directly, otherwise we solve the subproblem and add its solution to the table. Bottom-up approach. Try solving the subproblems first and use their solutions to build on and arrive at solutions to bigger subproblems. This is also usually done in a tabular form by iteratively generating solutions to bigger and bigger subproblems by using the solutions to small subproblems. For example, if we already know the values of f41 and f40, we can directly calculate the value of f42. Some programming languages can automatically memorize the result of a function call with a particular set of arguments, in order to speed up call by name evaluation. Some languages make it possible portably. Some languages have automatic memoization built in, such as tabled prolog and J, which supports memoization with the M adverb. In any case, this is only possible for a referentially transparent function. Example: economic optimization, optimal consumption and saving. A mathematical optimization problem that is often used in teaching dynamic programming to economists concerns the consumer who lives over the periods and must decide how much to consume and how much to save in each period. Let be consumption in period, and assume consumption yields utility as long as the consumer lives. Assume the consumer is impatient, so that he discounts future utility by a factor each period, where let be capital in period. Assume initial capital is a given amount, and suppose that this period's capital and consumption determine next period's capital is, where is a positive constant, and assume capital cannot be negative. Then the consumer's decision problem can be written as follows. Subject to for all. Written this way, the problem looks complicated, because it involves solving for all the choice variables. The dynamic programming approach to solving this problem involves breaking it apart into a sequence of smaller decisions. To do so, we define a sequence of value functions, for which represent the value of having any amount of capital at each time. Note that is, there is no utility from having capital after death. The value of any quantity of capital at any previous time can be calculated by backward induction using the Bellman equation. In this problem, for each, the Bellman equation is this problem is much simpler than the one we wrote down before, because it involves only two decision variables, and intuitively, instead of choosing his whole lifetime plan at birth, the consumer can take things one step at a time. At time, his current capital is given, and he only needs to choose current consumption and saving. To actually solve this problem, we work backwards. For simplicity, the current level of capital is denoted as is already known, so using the Bellman equation once we can calculate, and so on until we get to, which is the value of the initial decision problem for the whole lifetime. In other words, once we know, we can calculate, which is the maximum of, where is the choice variable in. Working backwards, it can be shown that the value function at time is where each is a constant, and the optimal amount to consume at time is, which can be simplified to. We see that it is optimal to consume a larger fraction of current wealth as one gets older, finally consuming all remaining wealth in period, the last period of life.